This lesson deals with supplemental problem 4.7, parallel resonance. You can find this problem in the course ebook in the Chapter 4 supplemental problem starting on page 7. Given this parallel RLC circuit, could you determine its resonant frequency? If I sub p is 200 pico times the cosine of 2 pi 1240 kilohertz times t, and R is 1 megohm and L is 360 microhenries, could you solve for the value that this capacitor needs to be tuned to tune it to the AM radio frequency AM 1240? Then can you find the time domain value of V sub p and the current in each of these three elements? A circuit is at resonance when the input impedance is purely real. Because I have parallel elements here, let me find the equivalent admittance. That's going to be 1 over R plus 1 over j omega L and then 1 over j omega C. You could write 1 over j as minus j. I'll pull that j out. So I have a minus 1 over omega L and then omega C and then 1 over R. This is some equivalent conductance, and this is called susceptance. At resonance, Z equivalent is real, but so would the reciprocal be. Let's just take this expression and set the imaginary part equal to 0. And that's this term right over here, the susceptance. So minus 1 over omega L plus omega C, where omega is equal to omega naught, the resonant frequency, and that'll be equal to 0 when this quantity equals this quantity. Omega naught C equal to 1 over omega naught L. Cross multiply the omegas, get omega naught squared equals 1 over LC. Omega naught is 1 over the square root of LC. Same as the series resonant circuit. Divide by 2 pi and you get the resonant frequency in hertz. In this equation over here, we could now solve for the value of C. It's going to be equal to 1 over omega naught squared L. 2 pi times the AM 1240, which is 1.24 megahertz, quantity squared, times the inductance of 360 microhenries. That turns out to be 45.76 picofarads. A variable capacitor is made up of metal fins that are interwoven, so as you rotate the shaft, you move different amounts of area between the plates. This way you can make a variable capacitor, not over a very big range, but more in the picofarad range. Let's next solve for our time domain voltages and currents. Let's transform our circuit from the time domain to the frequency domain. Current source IFP becomes a phasor IFP with a magnitude of 200 picoamps and angle of 0. The resistor is still a resistor of 1 megohm. Now we can plug in the value of omega, which is 2 pi times 1240 kilohertz. I'm multiplying that by the 360 microhenries, I get J 2.81K. For the impedance, it's minus J over omega C, again using 2 pi times 1240K, and then times the value of C, which is 45.76 picofarads. I get a minus J 2.81. Again, our frequency is 2 pi times the value in hertz, and that's 7.791 megaradians. I want to find the voltage across this parallel combination. I could find the equivalent impedance looking into these terminals, and then just multiply that by the current. 1 megohm in parallel with these elements, so I'll take 1 megohm, and then take the product over the sum of these two elements. Product over the sum, but these are the same magnitude but the opposite sign. Denominator is going to be equal to 0, so this is going to be equal to infinity in parallel with 1 megohm. So just 1 megohm. Voltage across the parallel combination is just going to be this current going into the parallel combination. But that's just equal to this resistance right here of 1 megohm. We get 200 microvolts at angle 0. Now let's solve for the current that goes in this resistor. So I know the voltage, 200 microvolts at angle 0, divided by 1 megohm, which is 1 meg at angle 0, and you get 200 picoamps. In other words, all this current came into here because these two in parallel look like an open circuit. But there's still current flowing in it because there's a voltage across it. Take the 200 microvolts at angle 0 and divide it by the impedance of the inductor to get the inductor current. That's going to be 2.81K at an angle of plus 90 degrees. This turns out to be 71.17 nanoamps at angle minus 90. Do the same thing for the capacitor. The voltage of 200 microvolts at angle 0 and divide by the magnitude of the impedance, which is 2.81K, and now the angle is equal to minus 90 degrees because we're between the third and fourth quadrant. That becomes a ratio of 71.17 nanoamps. Angle of the numerator minus the angle of the denominator gives me a plus 90. These have the same magnitude, but they're 180 degrees apart. So what's happening here is all of this current from I sub p is flowing into here, and this current is flowing in here. There's actually no current between these two elements. Now this current is about 356 times bigger than this current over here in magnitude. So like we saw for series resonant, we could create very high voltages from a particular voltage source. Here we can create very high currents from a current source. Now if we add up all the power, it still sums to zero. Whatever came in went somewhere. We're actually stepping the current up. In this particular case, we're stepping the voltage up in the series resonant case. And lastly, we can convert now to the time domain by taking the magnitude of our phasor and the angle, which was 0 for the voltage, and putting the cosine of omega t between them. Same is true for the current and the resistor. Angle was 0. For the inductor, the angle was minus 90. And for the capacitor, it was a plus 90. A couple observations. Magnitude of Y equivalent has its minimum value at F0, because the things that were in parallel with the resistor cancel. So when things are in parallel, things go down in value, but when we had the two reactive components canceling each other. The reciprocal, which would be Z equivalent, has a maximum at omega naught. What that means is that that current flows into the largest value of impedance at omega equals omega naught. This is the front end of an AM radio receiver, where the antenna is this current source that's flowing into a parallel combination, but by tuning the capacitor, we can create the largest impedance seen by that current source to create the largest voltage, so then we can amplify that and listen to it. The second footnote here is how the currents are flowing in that circuit. And this is supplemental problem 4.7, parallel resonance.